Okay, and now for some examples where hopefully things will make a bit more sense. Okay, that's an exam. These would be 3 exam questions. So, sketch the rectangular lamina. So lamina just means it's a 2-dimensional thing. We treat it as a 2-dimensional thing. With vertices 0, 0, 2. Okay, so we have 0, 0 is a point on it. 2 along the x, 0 along the y is a point on it. 0x, 3 along the y is a point on it. And finally, 2 along the x, 3 along the y is also a point on it. Behold our lamina. Okay, so this I'm calling it box. Suppose the density at each point is given by 2x squared y, assuming SI units, so that's going to mean our answer at the end is just kgs, because we're going to find the mass of the lamina. Okay, so how this works is you first, so this box here refers to this whole thing, so we're going to find the mass of a strip at x. So fix a constant, you're treating x like a constant, so this is a little bit like partial integration actually, a little bit. So this is x, and we're going to find the mass of the strip going from y equal to 0 up to y equal to 3. Okay, dA, by the way, is dx by dy here, okay? And x and dx are constant along the strip. The mass of the strip is given by, now remember we're adding up loads of different things. We're adding up from y equal to 0 to y equal to 3. And what are we adding up? We're adding up rho xy, which is 2x squared y, times dA, which is dx by dy. Now, along the strip, and this is something we're going to get used to, along the strip, well, 2 is certainly a constant, and along the strip x is fixed. So that's the way, it's a little bit like partial differentiation. X is fixed, so x squared is a constant. And the width dx is also a constant, so I can pull all these out. And what I'm left with is integrating from 0 to 3 y dy. Okay, so this is going to be the mass of the strip at x. Now, how do you calculate this integral? Well, how do you calculate integrals is you anti-differentiate and then you do top limit minus bottom limit. Now, to anti-differentiate y, probably the easiest thing is to see it as y to the power of 1. And so you're talking about, you got your constant 2x squared dx, and then the antiderivative of y is y squared over 2, and we're going from 0 to 3. And now we substitute in our top limit minus bottom limit, 2x squared dx, and we have 2 squared over 2 minus, 3 squared top limit over 2 divided by 0 squared over 2. This is a, this is the top limit, this is a 3 here. And then you get 2 over 2 is 1, so you get 9x squared dx. Now, you might notice that the mass of the strip gets bigger the bigger x is, and that's because the density is proportional to x squared. As x gets big, certainly between 0 and 1 anyway, x squared gets big. Now, the density at x equal to 0 is 0, so actually the mass of this strip at x equal to 0 is just 0. In any case, even at x equal to 2, this is 36, so at x equal to 2, the strip at x equal to 2 is 36 dx. Dx is really, really small, so it's still very, very small. And in fact, m is not good notation here. I'm going to say the mass of the strip. Now, it's a very, very narrow strip, so its mass is very, very small, but it has a mass nonetheless. This is the way I want to think about it. And now what you want to do to find the mass of the whole lamina, you add up the mass of the strips from x equal to 0 to x equal to 2, and that's the same as integrating from x equal to 0 to x equal to 2. And what are you adding up? The mass of the strip, which is 9x squared dx. Happy days. This isn't too bad of an integral to do. So let's anti-differentiate, fix the 9, and the antiderivative of x squared is x cubed over 3. And you want to do top limit minus bottom limit. So we get 9 over 3, 2 cubed, minus 9 over 3, 0 cubed. Substitute top limit. Remember, you can it's a video, you can pause me. And then 9 over 3 is 3. 3 by 8 last time I checked was, is it 24? I'm kind of a bit stupid there. 3 by 8 is 24, yeah. And then we're saying SI units kg. Now, is that really so scary? If you understand what we're doing, it isn't. If you're trying to follow, otherwise, yeah, it is difficult. But what you're doing is you're finding the mass of a lamina, break it up into two problems. Find the mass of a strip at a constant x by adding up from y equal to 0 to y equal to 3. All these things, this is kind of like the mass of a little particle. All of them are tiny. So if you're adding up, there's infinitely many of them. They're infinitely small. That's integration. And then once you find the mass of the strip at x, add up the mass of all the strips from x equal to 0 to x equal to 2. That's that. Okay, let's do another example. Sketch the triangular region with these vertices and find the centroid of the region. Indicate the position of the centroid on your sketch. So we've got 0, 0. Now, one thing we have to be clear, right? Go back to this. It is a two-dimensional object. We're not just going around the edges. Okay. Similar story here. We're not just going to be going around the edges. So 4 along the x, 0 along the y, and then 4 along the x, 4 along the y. And our job here is to find the centroid of this. Now, if you just use a formula, you're kind of not getting the point. We're showing you where those formulas come from. Okay. Indicate the position. Okay, find the centroid. Okay, let's go. So first of all, we'll find, so I'm writing this thing as the integral of, over the triangle of xdA, okay, over A. The area, it's probably fair enough that you just write it down. I mean, the area is half the base by the height. The base is 4, the height is 4. It's reasonable to just say it's half of 4 by 4. I'd say that's okay. I'm not going to explicitly ask you to use integration to find that area. To find the contribution to the sum, fix an x between 0 and A, and find the contribution to the sum, xdA, or the contribution to this sum just from this strip. And things get a little bit more tricky here. Okay. Right, the question is, how far do we integrate? So we're adding up xdA, which is x dx dy. So here, the dA is dx by dy. Why is that? This is zoomed into the max. dA, the area of that little bit, is dx by dy. Okay. And we want to find the contribution to the sum. Now, unfortunately, the thing we said the last day, oh, we found the mass of the strip. That's gone from us, unfortunately. So we just have to say the contribution to the sum from this strip. Now, we know that we're starting here at y equal to 0. But the problem is, how far are we integrating up to? Well, that depends on what x is. So where we're integrating up to should be a function of x. And the question is, well, what is it? Now, some of you in previous years have been very good about your, I don't know, the aspect ratios or something. And you said if that's equal to that, then this is equal to this. This distance is x, so this must be y. But in general, it might be a little bit more complicated than that. And my recommendation is to look at this curve here and say, what is it? Well, it's a straight line. Y is equal to mx plus c. What is the slope? Well, you can just look at it as rise over run. It's 1. and c is where it cuts at 0, so it's 1x plus 0, in other words it's x. So at each point along here the y coordinate is equal to the x coordinate, so if this is x, the y coordinate here must be x as well. Now maybe rewind the video and just go over that again, that you understand that the y coordinate here is given by mx plus c. Mx plus c is x, so that means everywhere along here the y coordinate is equal to the x coordinate, and if this is the x coordinate, if the x coordinate is fixed at x, it goes up to y to the x, so we're integrating from 0 to x. Okay, now along this strip x is a constant. X does not change along this strip, similar to partial differentiation. Dx, the width of it does not change, so what we're left to integrate is from 0 to x dy. Now this dy, if you really followed what was going on in the two previous videos, you'd understand that integration is adding up loads of little bits, and this is adding up loads of little bits of y. So the integral of just dy is adding up all the little bits of y. You should just get y. Now if that's a little bit tricky, and it is because this is an integral, not an antiderivative, say, well, what are we anti-differentiating? Well, it must be 1. And what do you differentiate with respect to y to get 1? The answer is y. So the antiderivative here is y. And we're integrating from 0 to x. Okay, and now we do top limit minus bottom limit. So we get x dx times, so substitute in for y, substitute x, minus substitute in 0, and we get x dx by x, which is x squared dx. Now we're adding up x times dx dy, and you can see that if x is 0, there's nothing to add up, and this would be 0. And if you're adding up the x coordinate by dx dy, when this thing gets long, when you're adding up over, like the x is the same, but when you're adding up over a longer distance, it's going to be bigger, and that's the case here. As x gets bigger, x squared dx gets bigger. Okay, so this is the contribution to this big sum from the strip at x. Now sum along all the contributions of this. So that's the contribution to the sum from the strip, and now add up the contributions to the total sum from x equal to 0 to x equal to 4. And that will be what we call integrating over the box x dA. So we're going to add up the contribution to this total sum from x equal to 0 to x equal to 4. Each strip is giving us x squared dx. And notice again the integration, we're not really pushing it too hard. So how do you calculate an integral? You anti-differentiate. The antiderivative of x squared is x cubed over 3. And you're going from 0 to 4, so substitute in top limit minus substitute in bottom limit. And we can pause the video whenever you want. It's 4 cubed over 3 minus top limit 0 cubed over 3. 4 cubed is 64, so you get 64 over 3. Okay, so therefore this the x coordinate of the centroid using the formula is this integral over the triangle. Sorry, this should be a little triangle, shouldn't it? X dA, which is 64 over 3 divided by 8 to get 8/3. And that should be somehow familiar to you in formulas you know about the centroids of triangles. Okay, now if you were, you could probably be a bit brave here and use symmetry, because this thing is symmetric. We won't do that. So we're going to do this again with this one. So again, we're going to fix x between, now we need to add up over this triangle y dA. So we're going to fix an x between 0 and 4 and sum y dx dy, because dA is dx by dy, from y equal to 0 up to y equal to x again. So this is like the contribution to the sum from that strip, is add up from y equal to 0 to y equal to x. What are we adding up? Y dx dy. Now along this strip, dx is a constant, so I'm going to take that out. And I'm integrating from 0 to x. What's left? Y dy. How do you calculate an integral? You anti-differentiate. If you're a little bit confused about the antiderivative of y with respect to y, think of it as y to the 1. So you get dx. Antiderivative of y to the 1 is y squared over 2. And you're going from 0 to x. And now you do top limit minus bottom limit. You will get again, remember you can pause me if necessary. So top limit, instead of y squared, substitute in x for y, it'll be x squared. And then the other one, it'll be x. So you have x squared. And then the other one, substitute 0 in to get that. So this is x squared over 2 dx. Now again, this is bigger. So we're adding up y by a little area. Now obviously, if you've got like say this sum here, it'll be the same as this sum plus a little bit extra. So the bigger that x is, the bigger you're going to get over here. And it's the same. Why it's x squared over 2, I'm not so sure. I don't think I can answer that. Okay, well anyway, we want to add this up from x equal to 0 to x equal to 4. Okay, so this is x squared over 2 dx. That's the contribution to the sum, y dA, over the triangle from this strip. So now add up the contributions from all the strips from x equal to 0 to x equal to 4. And that will be our integral y dA over the triangle. So add up this, add up this, the contribution to the sum at a strip, and the strips go from x equal to 0 to x equal to 4. Here's the first strip, and there's infinitely many. They go from 0 to 4. Here, well, what's going on with the 2? Well, divided by 2 is the same as a half, so that's a constant, so I'll fix it. And then I'm left with the integral from 0 to 4 x squared dx. And then, again, it's not the worst antiderivative in the world, because the antiderivative of x squared is x cubed over 3. And I'm going from 0 to 4. Top limit minus bottom limit, you get a half. Let's see. Substitute in top limit, you get 4 cubed over 3. Minus substitute in the bottom limit, 0 cubed over 3. That comes out to be something like 64 over 6. And then divided by the area, which is 8, you get 4/3. So altogether, we've got that the centroid x bar, y bar, x bar we found was 8/3. Y bar we found was 4/3, and now we're going to indicate that on our sketch. Now 8/3 is getting close to 3. Now this isn't even to scale, so it's not too important to just do it roughly. So kind of 3 might be around here actually. So 8/3 somewhere back here, and then 4/3. Well, that's probably a bit more tricky to do. So I'd say that this is 2, so 4/3 is kind of, that would be 1 maybe. So 4/3 somewhere like this. So something like that. It's not a bad shot at it actually. Okay, so yeah, that's how you calculate centroids. If you use the formula, you're actually implicitly using this kind of calculation. That's where the formulas come from, by doing these calculations. And I think this manual contains a number of those calculations if you want to see where those formulas come from. Okay, I think we have time for one more example. The second moment of area of a triangle. Right, let's see what we got. Sketch the triangular region with vertices 0, 0, 1, 0. That's 1 along the x, 0 along the y, and 0, 2, which is 0 along the x, 2 along the y. Right. So we need to add up y squared dA over this triangle. So the usual crack, fix an x between 0 and 1. Now this, thankfully, it is a sum, but what you can actually talk about is the second moment of area of this strip. So that's actually nice to be able to talk about. Right, now the question is, how far do we go? So we're adding up from y equals 0, and the question is, well, how far are you going? Well, it depends. When x is 0, it's 2. When x is 1, it's 0. So what I would, if I were you, and there's other ways of getting around this, but I would say that I don't think there are other ways around it, to be honest with you. This is a line, and therefore the y coordinates at each point are of the form mx plus c. So therefore, now the slope, now if you got the picture in front of you, you don't have to go for the slope formula, that's a bit daft, just do rise over run. And you have to be careful about the sign. However you do it, this one is going down, the sign is negative. Okay, now if you want, you can just bang in the negative, and then just say, oh, what's the rise is 2, and the run is 1. That's perfectly okay. Alternatively, if you go from here to here, you say that the rise is -2 and the run is 1, so you get -2 over 1, which is the same as this. Alternatively, you actually go backwards and you go, the rise is 2, but the run is -1. And that's actually a thing that probably is a good argument as any, that minus a over b, which is a way of calculating this slope, is the same as minus a over b, which is the same as a over minus b. That's just a side remark. All those things are the same. C is where it cuts the y-axis, which is 2. So you get y is equal to minus 2x plus 2. I'm going to turn that into 2 minus 2x for reasons that will become clear. We're going to be a little bit tight on time on this, so we better drive on. So we're going to find this, it says the contribution, we're actually going to find the second moment of area of that little strip. So how will I call this? I can call it whatever I want, I suppose. I'll say I'll forget about the xx of the strip. Second moment of area of the strip. So it's equal to, add up from y equal to 0 up to, well, we found that the y coordinate depends on the x coordinate according to this. So you add up to y equal to 2 minus 2x. And we're adding up y squared dA, and dx is dx dy. Now this time, just to save some space, I'm going to fix the constant now. Along here the width is constant, so that's dx, and then I'm just left to integrate y squared dy. The integral of y squared with respect to y is y cubed over 3. And now I'm going to do top limit minus bottom limit. So how am I going to handle this? What I'm going to say is, okay, this is divided by 3, that's multiplied by 1/3. I can take that out as a constant if I want. And now substitute in the limits, I forgot about the limits, 0 and 2 minus 2x. So substitute in 2 minus 2x, you will have 2 minus 2x cubed minus 0 cubed. And this is equal to, we could write this as 1/3 2 minus 2x cubed dx. That's the second moment of area of this little strip. If x is equal to 1, this thing is equal to 0, there's no strip, and it's actually at its largest at x equal to 0. Now we need to integrate this. This is the second moment of area of a single strip, and we need to add up the second moment of areas of the strips from 0 to 1. We need to integrate this from 0 to 1. If you're very good at integration, this is actually easier to do with a substitution, but we're going to do a manipulation. I'm going to multiply this thing out carefully. Now I'm going to go fairly quickly because I've only got so much time on the video, but 2 minus 2x cubed is the same as 2 minus 2x times 2 minus 2x times 2 minus 2x. So this is 2 minus 2x, and then you carefully multiply this out. 2 by 2 is 4. You get a minus 2x by 2 is minus 4x, and you've also got 2 by minus 2x. That's another minus 4x, you get minus 8x. And then minus 2x by minus 2x is certainly plus, and the x by x, the 2x by 2x is 4x squared. Okay, and off we go again. 2 by 4 is 8. 2 by minus 18x is minus 16x. 2 by 4x squared is 8x squared. Minus 2x by 4 is minus 8x. Minus 2x by minus 8x is plus 16x. I appreciate this is fast, but you can do this yourself. This isn't too difficult for you. Minus 8x cubed. Tidying it all up, I get 8 minus 24x plus 24x squared. Ooh, I'm missing something. Minus 2x by minus 8x is plus 16x squared. Yeah, so this is plus 24x squared, and then finally minus 8x cubed. What am I doing? Well, if I need to anti-differentiate this, I can only do it directly if it's a sum. This isn't a sum. You can't just start anti-differentiating the 2 and the minus 2x because it's cubed. It's just not, it's wrong. So I recommend that you multiply it out. Okay, so the second moment of area of the whole triangle is found by adding up the second moment of area of the strips and all of them from 0 to 1. And the second moment of area of each strip is 1/3 2 minus 2x cubed. Because of time, I'm going to write this. And I got my dx knocking around as well. Let's go. Fix the constant 1/3. And how do I anti-differentiate these? 8 might catch you. What do you differentiate with respect to x to get 8? 8x. Fix the minus 24. The antiderivative of x is x squared over 2. Plus fix the 24. The antiderivative of x squared is x cubed over 3. Fix the minus 8. The antiderivative of x cubed is x to the 4 over 4. Again, you can say, oh, I don't just use the formula. Where are the formulas coming from? This is what this is about. And now we do top limit minus bottom limit. Now I will just use all red here. So substitute in top limit. 8 by 1 minus 24 over 2 by 1 squared plus 24 over 3 by 1 cubed minus 8 over 4 by 1 to the 4. Take away, substitute in the 0. But look what happens when you substitute in the 0. 8 by 0 is 0. Minus 24 over 2 by 0 squared is 0. Plus 24 over 3 by 0 cubed is 0. Minus 8 over 4 by 0 to the 4 is just minus 0. So that doesn't contribute anything. Now in general, when the limit is 0, you can, like for example, if you get an exponential or if you get a cos of 0 and exponential of 0 are about 1, you have to be a bit more careful. And I think I'm going to go to the calculator if I can find it. Yep. So I get 1/3. Now don't put 8 by 1, don't be a donkey, that's just 8. Similar story, this is just minus 12. Similar story, this is just 8. Similar story, this is just 2. And we get, after all of that, 2/3. If there were units and there were SI units, it would be units of meter to the power of 4, as you should know. But that actually is also here because this is meter squared by meter squared, which is meter to the 4. Okay.